Hello everyone, my name is Kalina and I'm a student at the American University in Bulgaria. In this video, I'm going to present you two thermodynamics experiments. The first is about superheated water. Water is a polar molecule where the centers of positive and negative charge are separated, so molecules will align with an electric field. The extensive hydrogen bonded network in water tends to oppose this alignment, and the degree of alignment is measured by the relative permittivity. Water has high relative permittivity of about 80 at room temperature because polarity shifts are rapidly transmitted through shifts in orientation of the linked hydrogen bonds. In physics, superheating is the phenomenon in which a liquid is heated to a temperature higher than its boiling point without boiling. Superheating is achieved by heating a homogeneous substance in a clean container free of nucleation sites while taking care not to disturb the liquid. This may occur by microwaving water in a very smooth container. Disturbing the water may cause an unsafe eruption of hot water result in burns. Water is said to boil when bubbles of water vapor grow without bound, bursting at the surface. For a vapor bubble to expand, the temperature must be high enough that the vapor pressure exceeds the ambient pressure. Below that temperature, a water vapor bubble will shrink and vanish. Superheating is an exception to the simple rule. A liquid is sometimes observed not to boil, even though its vapor pressure does exceed the ambient pressure. The cause is an additional force, the surface tension, which suppresses the growth of bubbles. What makes superheating so explosive is that a larger bubble is easier to inflate than a small one. Just as when blowing up a balloon, the hardest part is getting started. Once a bubble does begin to grow, the surface tension pressure decreases, so it expands explosively in a positive feedback loop. In practice, most containers have scratches or other imperfections which trap pockets of air that provide starting bubbles. That's why only a smooth container of purified liquid can reliably superheat. Now let me show you the experiment. In the experiment, one observes that when the rough particles are added, water starts to boil again, which means that heat is available despite the absence of an external heating source. This heat must come from the water itself, whose temperature necessarily decreases in the process. One must conclude that before the rough particles were added, the temperature must have been above that required for boiling. Finally, the demonstration gives a tangible example of thermodynamic metastability. Now let's continue with the other experiment, which is about supercooled water. Supercooling, also known as undercooling, is the process of lowering the temperature of a liquid or a gas below its melting point without it becoming a solid. The supercooling of water can be achieved without any special techniques other than chemical demineralization down to minus 48.3 degrees Celsius. Supercooled liquids are trapped in a metastable state even well below their freezing point, which can only be achieved in liquids that do not contain seeds that may trigger crystallization. Supercooling was discovered already in 1724 by Fahrenheit, but even today the phenomenon remains a subject for intense discussions. Over the last 60 years, the very existence of deep supercooling has led to speculations that the internal structure of liquids could be incompatible with crystallization. Now, let me show you the experiment in which we can see clearly the rapid crystallization. In this temperature range, the no man's land of water's complex phase diagram, the supercooled liquid rapidly crystallizes, making measurements difficult. Now let's see the experiment once again. thank you very much for your attention, and I hope that you learned something new today.